Right, okay, variables. Variables, storage location. We refer to that location in memory using a name. It's called a variable because its value can change. We assign a value to a variable using equals. The left-hand side is where we're going to store something, so that's where we put our variable name. The right-hand side of the equals is what we're going to store, which might be a simple value, like a constant value, or it might be a calculation, which the computer would do first, or evaluate before we store it. That could actually be, oops, oh my board's awful. That could be the result of a function call. So if you get given something like that, what's actually happening is, we're saying, right, we're going to store something in name. We know it's stored because of the equals, but we don't know what because we've got to run this or execute this function first. Once that function's finished, it will return whatever value it's obtained, and then we can store it. If we've got a constant that is similar to a variable, it has a name, we can assign a value to it, but when we've got a proper constant in a programming language, its value will never change. Okay? We use constants, so instead of doing something like that, we can make a literal value more meaningful. Okay, assuming someone knows what PI means. Okay, so that's constant. When we're dealing with inputs and outputs, standard way of showing that, if we need to get some input, and you will see this in the mark schemes, don't ever do this. You can't do that. Input has to go somewhere. So they will always expect to see something like that where you say, like, store the input somewhere. Make sure you give them some indication of what you want them to input. On previous questions, that's been worth 1 or 2 marks because you've requested the correct information and you've stored it. Okay, so you've got to be careful. When you're doing output, in general, they want you to perform nice output. So if I was to write this data back out on the screen, I could just do that, print data, but what would be nicer is to put a message with it. So I can use concatenation. So I can say, you entered and that plus does not mean add, it means join this value to this piece of text. Okay? You can use more concatenation afterwards. So you get like a bit of text, a value that you've retrieved from a variable, plus another bit of text. Okay? You'll generally get that from a bullet point in the question if they're asking if there's some pseudocode. That is one of your easy wins. Okay, to do the input and the output, even if you can't work anything else out. Right, the 3 constructs. Sequence. That is just putting the statements that you need to do your task, your algorithm, in the right order. So, obtain some input before you do a calculation with that input. It would seem obvious, but you can make some really dumb mistakes when you're programming. The other thing, selection. This is making decisions. So we've got if else, we have got if and else if, where you can keep asking extra questions. There is also another form, not all languages support this, Python doesn't, called switch. It's basically a C-based language thing. And you have a value, and then you have cases. And you have statements that you do. Okay, so that is like organising using ifs, but you only have to put the thing down once. So I could do it like this. I could say if value equals that, then do this. Else if value equals 2, do whatever. So a switch statement is really just a simplification of a load of if, else if, else if, else if. Okay? The final construct is iteration, which is your loops, where you identify actions or statements you want to repeatedly do. There are 3 basic loop structures. If you know how many times you want to do something, you've got a counter or something, you can use for. Okay, so you start positions, last value, and then you do your statements that you want to execute. You'll often do that with an array. I'll come back to arrays. You can do a while loop. I'll do the same loop. But with a while loop, you must make sure that you put something inside the loop that will eventually allow the loop to stop. So with a while loop, put an L, we're saying while I, you just read it like English, which is quite nice, while I is less than or equal to 10, do the statements that are inside the loop. I is going to increase by 1 each time, so eventually that's not going to be true, and then we will carry on down there. The other loop format is a repeat until. So you do your statements inside, and it's sort of like the opposite of the while. So I'll do the same loop again. So with this one, we do our statements and then we test at the end. So we keep doing this until something's true. So you see that the logic is slightly different to the while loop, it's like the opposite logic. So we're saying while I is, well, less than 10, keep doing the loop. If that becomes true, then stop the loop and do the statements afterwards. The big difference between while and repeat until you always do your code before you test to see if the loop's over. So this will happen once at least. Repeat until loops is how you would set up a password login. You want someone to try and log in at least once, so you know you're going to have a password once test. With a while loop, that can happen 0 times. So it might not be you do the loop at all, depending on the condition. If I'd have set this to 50, then that loop won't happen at all, and we'll just jump straight down. But if I set it, the repeat until to 50, that loop is still going to happen once. And obviously the big difference in the for loop is it's a counter. So you're saying I like them 10 times. Okay? So that's your 3 constructs. String manipulation. Oh, I'm a nightmare with this board. I still prefer it to using the computer. Right, string manipulation is anything where we are processing string values, text. Okay, so if we have some text, and there are basic ones, it's just going to be pseudocode, it's different in different languages, but there are functions that we apply. That's what string manipulation. One of them is concatenation. So if I do A equals N plus X, Y, Z, that will create a string that's got A, B, C, D, E, F, G, and then X, Y, Z at the end. That's the basic one. I might want to get a portion of a string for whatever reason. Maybe I want the first 3 characters. So I might say print, and I can do it lots of different ways. It's up to me, but dot notation is the simplest way of doing it. If I say, let's get a substring, so a portion of that string, and then I can put 2 values. So I can put, where do I want to start? Now, bearing in mind that we use 0 indexes, if I say start at 0, get me the next 4 characters, that would display A, B, C, D. Okay, so this is the start. That is how many. So that's substring. You can do a lot with substring. You can get the left of the end of a string, right end of a string. Okay. The other things that you might need to do and things that we have to worry about is you might say n dot upper or uppercase or whatever wording you want, but upper, that would give us that. Doesn't alter the string, but it gives us the uppercase version. Now that's super important when we're comparing strings, because if we do something like this, I'll put the whole thing. And I put double equals to mean compare. So if I put that, that would return false because I put a capital A there and we've got a little a. If you're not bothered about case sensitivity, what you could do is you could change this and make use of, you could say if n dot upper, if the uppercase version equals, and then you'll get a match. Okay, so if you've ever got to compare strings and you're not bothered about case sensitivity, and we tend to not worry about case sensitivity unless we're making the names of variables and things when we're programming or passwords. It's when we tend to worry about case sensitivity. So you can force to uppercase or lowercase, whichever you feel happiest doing. Okay, so always bear that in mind. That could be something they check and test you on in an exam question. Okay? Right, so other things that you can do, you might ask for the index. So you might say n.index, and you might say the index of B. So in this case, I'll put lowercase, again matching, that would return 1. Because B is at index 1, 0 index. If in doubt, if you're going to be messing about with a string or an array, write index positions down so that you can refer to it and you can check. Okay? I'm trying to think of any other string ones. There are loads of string ones, but it's just the most common ones. I'll come back to you if one comes back to me. Right, file read. Oh, I know, there is another one, split. Let's say we've got a string like this. comma separated values. What I might do is I might say n.split. You'd be amazed how often we do this when we're programming. And we say, okay, find the commas and split this string up for me. You can write a function to do this, but it's quite a laborious process. So most languages support this now, so we'll accept this in pseudocode. What that will give us is an array. So it'll look for all the commas and it'll say, right, okay, and it'll give us this structure. So this is how you might get a set of data into a computer ready to sort it, search it, etc. Okay? Once we've got it in an array, we've only got the number data, which is what we want. We don't want all the commas. They would just separate us for us as humans. Okay? So we can split it into an array. You might need that feature. Right. The other thing, files. Obviously, files are closely related. We only really talk about text files, but you can have binary files and read files in a binary way, but we'll focus on just basically reading and writing. And it's pretty much identical to how we do input and output of text. So input and print. So the key things you've got to do, you need to open a file. And you need to say that you're opening it to read or you're opening it to write. So let's have a look at. So you can just say open read, give your file name. Okay? When you're writing pseudocode, as long as the intention is clear, then it doesn't matter how you present it. Okay? Because you could write that as this, you could just say open file.text. And then put read or something like that. So you might do it as two parameters. It doesn't matter as long as it's clear. The key bit is that we store a reference to the file that's been opened. And then we can just say, let's say we've got lines of text in this file, we would just say read line. And that will read a line of text from the file. And then we can put that in a loop if we need to keep reading. You might put something like this. No, you might put something like this. You might say not end of file. Okay? And you might, every time you read, that moves the file pointer on. And you just put in there, you say line equals f.readline. And then print that line out maybe. Just, you want to print the contents of a file. Okay, and that would read in. What you must do whenever you've opened a file, you must close it at the end. So you must say f.close. The process of writing to a file is probably simpler because you don't have to check to see if you're at the end of a file or anything. So you might do f equals, and I'll just do this long format. Open write. Give the file name. And then if I want to write something out, I'll just do write line and whatever I want to. Whether it's a piece of literal text or whether it's a value of a variable. If I needed to write an array, I'd do a loop. So let's say I've got an array with 10 items. I might do for I equals 1. Let's do 0 to 9. So that's 10 items. And I say f.write list I. So that writes out each one. Just like when we open, we need to make sure we close, but it's actually more critical when we're writing to files. Because when we write to files, we don't write directly to the storage device, we write to an area of memory called a buffer. The close makes the software flush the buffer to the file. That is a common mistake. On when you're writing files, it's forgetting to close it. You're just assuming that it's going to get closed, and you end up with an empty file. File will get created, but it'll be empty. Okay, so that's the basics of files. Right, next thing, quick recap on SQL as we're programming. Structured query language, used to interrogate databases. Basic structure, you use the keyword select to say what fields you want from your database. You only need to extract the things you want. So that's the first line, the select clause. Then we have a from clause to say what data table is this coming from. So this might be from a data table called users. And that would be a basic query. That would retrieve the name, age and group of every single user in the user table. If we want to restrict it, we can use a where. So we can put a condition. So we might say where group equals Dave. So that would restrict the extraction of name, age and group, but only of the people who are in group Dave. If we want to order it alphabetically, this is the only other thing, we can have the order by clause. And then we just put the field, so that's what I want name, and then I would say I want it ascending, or I would put a descending. So A to Z or Z to A. Same with numbers. Ascending means small to big, descending means large to small. You can put and, ors and nots in the where, just like you can when we're programming. So I might say all the members of Dave whose age is less than 17. I don't know what this database is about. Okay, so that would give me a filter. If I want everything, I want all the data, I can put a wildcard. So I could say select star. That retrieves the entire contents of the database. I can use wildcards in my where clause. So I could put DA star. So that would retrieve anyone whose group starts DA star. If I want to go a little bit further and say I want any group, I don't know why I want this, but I've got it now. Any group that's got DA in their name, I could go asterisk DA asterisk. So that would say, right, you know, I don't care what comes before DA and I don't care what comes after. Getting the database to do all the filtering work for you. That's the whole point of SQL. It's not meant to be complicated. It does get complicated, but at a basic level, retrieving data from a database is quite straightforward with SQL. It's the system we use. What's the next topic? Right, arrays. Just quickly go over arrays. I've mentioned them already. Right, if we need to create or declare an array, you don't have to use the keyword dim, but we need to like indicate that we've got an array. So if we say 10 items, and then just say what type it is. Okay, so that would create an array called array containing 10 items of type integer. Remember the key thing about an array, you refer to it with a single name. Let me change that to 4 items so it makes the box smaller to show. It is a fixed size. It contains information of one type, so in this case integer, and we can access items in the array, or elements as we call them, by putting the name of the array, square brackets, and then the index. So if I was to do this, I would be saying, I've got a store operation. I would be saying, right, okay, where am I storing it? Right, there's an array, and I want to store it at location 2, index 2. What do I want to store? 19. So that value will be overwritten with 19. So this is the key bit, the name and the index. And you can just then use it like a variable. What's really flexible about it is that can be a variable. So a common thing that you might need to do with an array once you've created it is initialize it. Set it to 0 or some predefined value. So you do that with a loop. So you can say for I equals 0, because you know how many items are in the array, then you can say array.length. Now what you've got to be really careful about, this has got 4 items in it. Oops, that's bad. But the last index is 3. So if you're going to do a for loop, you would tend to say that. So you say, oh, I want 0, 1, 2, and 3. Which is why I would always say, if you get given an array in an exam, and you're asked to write some pseudocode for it, write the indexes down, and then you can see what your limits are. Okay, so this would allow us to then say array I. So we're saying, right, index whatever the value of I is, that is the index we want to access. I wish my board was a bit cleaner. So I've just used a standard loop that goes a certain amount of times, and that's how I'm manipulating the array. So I'm just saying, right, first time round I will access index 0, next time round it'll be index 1, then it'll be 2, then it'll be 3, and that's where I'm going to stop, because that is 4 minus 1, which equals 3. Okay? Do working out. If you've got a 2-dimensional array, it's no different. So I'll do it over here. So you're just going to say, I'm going to call this one grid. And then you just put down your values. So I create an array that's 2D, called grid. It's going to store characters, that's single characters. It's going to be width 3, height 4. It's up to you whether that represents a column or rows. Okay? So that might represent an array looking like this. So I'm going to say the 3 is the number of columns. And then this is going to have 4 rows. So when I want to refer to a location in the grid, again, I'm going to write down some numbers. In general, that would be 0, 0. Okay? It's not like a graph in maths. So if I was to say grid 1, 2, I'm going to look up for column index 1, and then I'm going to look for row 2. So if I say that equals F, that's where I'm going to put the F. If I want to initialize a 2D array, I've got to initialize for each column every row. So I need a loop within a loop. So let me just do that. I'll do it here. Rub that up a little bit better. Right, so I would have I'll do it fixed for this one. So I'm going to say 0 to 2, and I can see, because I've written them down, that's what I want. And then I'm going to do a loop straight away. So I'm going to say for row equals 0, and the rows, I've got 1, 0, 1, 2, 3. So I'm saying, right, iterate or loop over each column, and then for each column, so I'm looking at that column first, I'm going to go, So I'm going to say grid, square bracket, and because it's 2D, I have to specify 2 indexes, for column and row. And I'm going to set them all to, for some unknown reason, B. So what I need to do, I need to say, finish off the row loop and finish off the column loop. Right, what that example actually highlights as well is indentation. So where I've got a block of statements I want to do, I indent, and then I come back when I've finished that block. There is nothing to stop you in the exam doing these dashes. And in fact, most modern development software these days will put markers. Visual Studio definitely does, Visual Studio Code does. We'll put markers to show you how blocks line up. Okay? So that's access arrays, quite simple. Right, functions and procedures. Both subprograms. A way of decomposing a task into component parts. Once we've decomposed that task, we can work on individual elements of a solution rather than trying to work out the whole solution. Using those individual elements to provide a full solution. So we've got procedures and functions. They have a name. So let's do a function first. So you have a keyword function to say that you're making a function or defining a function. You have its name, which we call an identifier, and then you have parameters. Now, if you've got, don't need any information, you don't have any parameters, but you still need to put the parentheses, open and close parentheses. If you want to add 2 values together, you will need to be given those 2 values. So that is parameter 1. That is parameter 2. These names that are given are the names that are used to refer to the two values. Okay? So I can say C equals A plus B. Because it's a function, functions return values. So I would say return C. And then I put a marker and say end function, or N. I'm just going to put N. Okay? In reality, you would not necessarily have to do it like this. You could make that simpler by doing this and not having that line at all. Okay, for this simple function. To use this function, we have to call it. So we might do something like this outside of the definition for this function. So we've got this function called add. I want to add up 5 and 7. And I'm going to store the result in F. So this is a good example of that store operator again. So we're saying, right, where are we storing something? Oh, in F, which we assume is a variable. What are we storing? I don't know. We've got to execute this function first. So we execute that function. We pass the 2 parameters. The function goes, returns an answer. That's what we end up storing. So if we was to look at that, using my maths power, F would have the value, hopefully, 12 in it. Okay? The only difference, really, between a function and a procedure is a procedure does not return a value. Okay? So when you've got a task that needs an answer, needs to work something out and return an answer, you're going for a function. If you've just got a task that just needs to do a job, and then it's done, then you can use a procedure. Okay? Right, data types. Right. I'm just going to get another pen that works, because I'm crying out.
Let's get this bread.
Still a bit of time. Right, data types. So we've got various data types that are standard. We have integers. What you'll get asked about data types is more what data type is suitable for a type of data. So this is for whole number data. Positive and negative. So if you're looking at storing temperatures or the time it takes to run a certain distance, that's probably not going to be integer data. But if you've got the number of people in a class or the number of votes cast, you would hope that that is whole numbers. So they would be suitable. You have then got your real numbers. The exam board will let you, because programming languages call them floats. Okay, these are where we got fractional parts. So anything where we have got, I don't know, a temperature 1.7 degrees Celsius, you'd want to store that as a real. Not really much else to say about that. You can also use it for stupidly large numbers, which you wouldn't fit into an integer. In general, a standard 32-bit integer can hold numbers in the range 2 billion plus minus. A floating point can hold numbers much bigger and actually much smaller. So if you've got astronomically large numbers or atomically small numbers, floats are suitable for that. You have got character. Character is for storing textual values, single values. These may be in the form of ASCII, like we traditionally used to have. Remember, that's the 7-bit code. And then extended ASCII is an 8-bit code. Okay, with 7 bits you've got about 128 combinations of noughts and ones, so you can represent 128 characters. Not many. Enough to get by with a programming language, but couldn't store European characters. Extended ASCII had European characters in it, plus a few more different symbols. But they are both hopeless for storing languages that are in use around the whole globe. So we've got another format called Unicode, which is a 16-bit code. Okay, so with 16 bits you've got 65536. 64K worth of characters. That's still not enough. So the way that Unicode actually works, you have a page as well. So you've got 16 bits for each page. But we can have 64,000 pages. So Unicode has actually been designed quite cleverly, okay, so that we can include all those aliens we meet as well and be able to record their languages, unless they use really strange character sets, which are humongous. They might laugh at us for using Unicode, but there you go. Right, so characters single value. Remember, you've got you might get asked, or you might have to remember in the exam, 65 is capital A, 97 is little a. The difference is 32. So if you can remember the capital letter, you've only got to add 32 to get the little letter. 32 is also space. 48 is digit 0. You just add 1 to get the others. Right, the other data type, string, is basically, you can think of it as a list or an array of characters. Super useful, lots of things are text. Strings. The other one is Boolean, true or false values. Useful when you've just got two polar opposites that you want to record. Right, so operators. Loads of operators. Some used in conditions, some used for calculations. So you've got your standard ones: plus, minus, equals, and divide. Just do what we do when we're doing maths. You've also got less than, greater than, less than or equal to, greater than or equal to. That we use when we're comparing. You've got not equal to, and you've got equal to. So this one returns true because these are comparisons. If two items aren't the same, that will give you a true result. If two items are the same with the equal, that will give you true as well. Right, you've got your logical ones which allow us to combine comparisons. So we've got not, so you can say not A is greater than B. Okay, once you start putting nots in there, it starts getting a bit mind-bendy. But we're saying like, right, if A is greater than B, that is true. Not just flips it, just like logical not does. You can put use and if you want to accept a range. So you're saying, if we've got a value A, we're checking to make sure it's bigger than 5 but less than 10. So it's within the range 5 and 10, but not including those. If you want to include those values, just put less than or equal to. So if you get asked to validate something, and they say, oh yeah, it's got to be within 5 and 10, or even if you're entering a score for a test, which was out of 10, between and including 0 and 10. That's how you do it. If you want to pick distinct values, so if you say if A is less than 6 or A is greater than 17 for whatever reason, okay, you're saying that you will accept the value of A if it's 5 or smaller or 18 or bigger. Okay, it's generally easier to do inclusive, unless they say in the question exclusive of those numbers. Okay, so these are your logical ands and ors. So these are, you can do truth tables to work these out, but they read like English. Okay, you're going to get an answer of true overall, because all these comparisons give you true or false, because they're Boolean, if both items are true. With this one, with an OR, if one of those is true, you get a true as the overall answer. Okay. Right, couple more that might come up in the exam. Our favourites, mod and div. They're both division operations. Mod gives you the remainder. Division gives you the whole number part, the integer. So let's do a little bit of work. So let's do 5 mod 3. So what we do is we divide 5 by 3, and with mod it would give us the remainder. So when you do that, what would the remainder be? You can do it, it's like a clock. 2. You just subtract it. And in fact, mod's really expensive because that's how it works. You just repeatedly subtract 3 until it goes negative, and then you add 3 back on, and that's your answer. That's how you can do it. Okay? So if I go, 5 minus 3, well that's 2. Okay? Minus 3 gives me minus 1. It's gone negative, so add 3 back on. It's difficult to detect, so we normally check for that. If I do 5 div 3, we're saying how many whole times did it go in? So with this one, it just gives us the answer 1. They work together. If you want to know if a number divides exactly by another number, the remainder will be 0. So you can test. If you need to know whether one number divides wholly into another number, you can use mod and look for a result of 0. If it's 0, it went in completely. There was no remainder. Okay, so mod's really important. The only other one is exponent. So that's like 2 to the power of something. So if I say 2 to the power of 3, if I write into, not all languages support the exponent. Yeah. Okay, some languages do, some languages don't. They have to provide a function to do it instead. So you might have something like this. Math.pow. And you would say 2, 3. But you can put that in the exam. So, but if that comes up in the exam, don't get scared. That's what that means. What are these bits? Right, data representation. If we get a binary question, it's got to be a go-to question. Binary to decimal, you just read the column headings out. So if I've got this binary number, it's just a 6-bit number. Write me columns, headings down, no one's going to laugh at you. So just add them up, 2 and 46 plus 32 must be 38. Just read it. If I want to write a binary number in hexadecimal, hexadecimal is equivalent to 4 bits. Because that represents the numbers 0 to 15. So if I get given this 6-bit number, work from the right-hand edge and identify 4 bits. We've only got 2 here, but you're basically saying there is an invisible 0 and another invisible 0. And then just read the numbers as if they were just 4-bit numbers. So this portion is 6. This portion is 2. So in hexadecimal, this binary value will be 26. To go the other way is even easier. So if I have F, A, 8, D, which is a 16-bit number, and I know it's a 16-bit number because each one of these hex digits is 4 bits. All I've got to do is say, well, what's F? 1, 1, 1, 1. What's A? Well, that's 10. So what's 10 in 4 bits? That's 1, 0, 1, 0. That's that one. Write down 8. Well, 8 in 4 bits is 1, 0, 0, 0. And if you're not sure, just write down column headings. So you're not like guessing. No calculator, so you've got to do something. Right, D is probably the worst one. That's 13. A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. So if I want to do 13, so that's going to be an 8 and a 4, because that's a 12, plus 1. And there's my number. So hex and binary are really simple to do together. If I want to write down a binary, a decimal number, that's the worst one. Decimal to binary. Because it's a human to computer format, and that's never easy. Right, so you need to know how many bits you're going to do. Let's say I'm going to do a 4-bit number. Because I don't want to do a massive one. So I'll write down column headings for 4 bits. So I have got 6 to write down. So I want to do 6 from decimal to binary. So I start with the biggest column and I just say, right, okay, can I fit 8 into 6? No, I can't. So I'll put a 0. Move on. Can I fit 4 into 6? Yes, I can. That leaves me with 2. Can I fit 2 into 2? Yes, I can. That leaves me with 0. Can I fit 1 into 0? No, I can't. You've got to check yourself, make sure you haven't got mistakes. If you started with an even number, make sure that the 1 bit is 0. Okay? What else have we got? If you get asked to write the number 6, not 6, let's pick another number. 48. No, let's do 47. If you get asked to write a decimal number straight into hexadecimal, write it in binary first. Okay? You could start dividing by 16, but you've got no calculator. You don't want to make it more complicated. So I'm going to do this. So that's 47 in binary. Easy to do the hex from that. That's F. That's 2. 2F. Okay? Well, it's up to you, but I recommended it that way, and don't try and start dividing by 16. Because it'll get unpleasant. Difficult to check. Images, or what we tend to call bitmaps. There are loads of compression formats, lossy and lossless compression for images. We have got GIF and raw bitmap, which are, well, raw bitmap is no compression. GIF is what we call run length encoding, where you count the number of consecutive colours, and instead of writing down every single one, you just say there are 10 green. So you can save space. It only works with simplistic pictures. If you keep changing the colour every pixel, and you use GIF to store your data, you'll end up with a picture twice as big. Because you keep them saying, oh, I've got 1 green, oh, now I've got 1 blue, no, now I've got 1 red, whatever. Yeah, whatever operation you do, you do not throw any of the data away. Don't worry about a specific form of lossless. What you're doing is saying, I am not losing any of the information. So the compression technique has to be something like run length encoding or dictionary encoding.
I've seen some lossless with the storage is far bigger than what it actually is.
Yeah. If the data that you're trying to compress with that method is not suitable for that method, yeah, you'll get a bigger file. So you've got to pick, there are different ways of doing it. Okay. With the lossy ones, you're looking for information you can discard. So for things like images, the brain is really good at interpolating images. It's why you can see pictures when you look at clouds and things, and you see patterns in random carpet like we've got, because you can interpolate. And actually you don't need all the colour information, so you can throw part of the colour away and part of the data away, but the brain's clever enough to reconstruct. So you can get big compression ratios if you throw things away. Same with audio. There'll be frequencies that you can't hear, throw them away. Don't need them, even though they're there. Right, so we have a pixel, which is a picture element. So a picture is made up of pixels. So you have a number of pixels wide and a height. When you save a picture, you need to record all this information. So you'll need to put this in. This is called metadata. Metadata is a thrown around term, but it just means data about some data. It's called metadata. So you will record the width and height. You then need things like how many bits per pixel. So this the range of colours we can represent. If we have one bit for each pixel, we've got monochrome image. So 0 represents a colour, 1 represents no colour. Well, it depends how you want to work it. We would then have with that a palette. So whatever the 0 and 1 represents, so it could be blue and yellow, it's just 2 colours. It could be red and black, it could be white and grey, depends on what you're representing. Okay?
This is in the metadata.
Yeah, this is all in the metadata. So this is all going in there. So width, height, palette. You'll see this on games a lot when they've got they've made one model and all they do to differentiate between the models is to change some colours. Different armour colour, that's it. So you can mess about with palettes to make it look like you've got more than you have. So 1 pixel is quite limited. Okay, monochrome display. If you're printing, you can use 1 bit for that. So the more bits, the more colours. If we use 4 bits, we can have 16 colours. If we use 8 bits, and this used to be like the standard excellent graphics on a PC, 16 colours. Because people used to have 4 colour graphics cards. A graphics card that could do 4 colours, amazing. And that was white, black, cyan and magenta. Really poor choice. Then we got 16 colour cards. Then we went up to VGA, which was 8-bit. So we could have 256 different colours on screen at once, but the palette could be bigger. You pick what all those numbers represent. So that's like just using a single byte. What we actually have adopted now is what we call 24-bit colour. Obviously, the more bits you use for each pixel, the bigger this file's going to be to represent it, yeah. So with 24-bit colour, we're using a byte of red, so you've got 256 values of red. You've got a byte for green. You've got a byte, oops, blight I put then, a byte for blue, which is what we commonly call RGB colour. It's how monitors are designed to represent RGB colour. So we use this format not only in images, but we use it for colour representation in HTML. And we write it in hexadecimal because it's really quite neat, because you've got a separate byte for each colour. So if you do FF0000, you're saying full red, no green, no blue. If you want to put a bit of red and blue together, you can do it quite easily, because they're independent. If you tried to do it in decimal, it would be horrible. Okay, so all these things can affect the size of an image. You might get asked to calculate that, but they've got to keep the numbers fair because you've got no calculator. So be dead careful with that. With audio, similar thing. Guys, with audio, you take an analog signal a waveform, and in order to digitize that, we have to sample. So we have to take samples. How often we do that is called the sampling rate. So that's the first part of the problem of digitizing sound, is picking a sampling rate that's fast enough. Now, if I was to halve the sampling rate that I've actually drawn on the board, when I come to sample this signal, I'm only seeing it at those points. And what's quite important is, if your sampling rate is too low, you miss information, frequency information. So you can see from there to there, according to the computer, at this sampling, that peak doesn't exist. So you've missed some information there. There we're not too bad, doesn't really matter. It's managed to pick that up, but you're missing the nuance. There is information there. Again, there, we have effectively missed that part of the waveform out. So, sampling rate needs to be high enough. Generally, it's got to be 2 times the highest frequency that you want to record. For music, we use 44,100 hertz. Because, in general, the highest frequency humans can... Gents, I am recording! Yeah, so I double my sampling rate so that I can get that detail. If I wanted to, if I was doing bat analysis, I was trying to listen to bats, some bats generate noises that are that high. So my sampling rate would have to be twice that. Quite a lot. Obviously, the more often you sample, the more data you're going to collect. So if you're sampling at this sort of rate, and this is per second, because it's hertz, so I will have 44,000 data items to represent 1 second of a piece of sound. The other thing is the bit depth. So that is for this axis. So the sampling rate controls how often we look, but the bit depth says how accurately you're going to represent this. If I use 1 bit to represent each one of these sample points, I can only say whether there was something or nothing. So that's no good. Okay? So the more I use, the more accurate I can represent it. So if let's say I use 1, 2, 3, 4. 4 points. I've got 0, I've got quarter, oops, only quarter. I can represent either the full sound, we'll not do that, we've got 2/3. So if I used 4 bits to represent these 4 values, so 0, 1/3, 2/3 and 1, I would have to, when I sample, approximate. So I would say, okay, that was probably there. That one, bit dicey, maybe up there. That one's up there. That one, probably there. That one, yeah, probably there. That one, maybe there. So when I look at this, I get a really poor approximation of that original thing. So I need to make sure that I've got enough bits per sample, okay, or the bit depth for this, so that I can accurately represent the range that that waveform's going through. Okay, and with sound, 16 bits. So we split that waveform into 65,000 different values. So that's reasonably accurate for what we're trying to do. You can start using more bits, but the more bits you use, the bigger the file's going to be that you generate. So with just this, so that's 2 bytes. So that's for 1 second of recording, 88,000 bytes. That's in mono. If you want to do stereo, double that. So that'd be 176 kilobytes per second. If you're doing Dolby 7-channel surround sound, multiply that by 7. So you've got to have a balance. You don't want to oversample, but you don't want to undersample. You don't want to use too many bits per sample, but in the same way, you don't want too few that you're just basically just going, and you've got no frequency information. all that information will go in as metadata as well to tell you what the format is. Yeah. Right, again with the compression, what you're doing is you're looking at frequency changes that the human ear wouldn't pick up. So you would say, like, if something goes like that, you might say, well, actually, this isn't how it works, but you might say, well, actually, we'll smooth it. We'll use a function to smooth it. What you'll notice, if you do compress something with MP3, which is really rough, you can tell the difference. If you listen to an MP3 version of a song, and you listen to a raw song, okay, in fact, if you look at streaming information, they use higher bit rates than this, don't they? So they've realised on the streaming that that's what they want to do. They want to make it higher quality. So they might have, like, I don't know, 192,000 bits per second. But you've got to remember, you've got to start dividing that up. In videos, the same. You're looking for videos just like pictures. You're looking for, if you use MPEG compression, you're averaging a group of pixels together and saying what colour are they. And you can alter the quality on that. So you could, if you really wanted to, you could say, let's just split the screen into quarters. What's the average colour in each quarter? If you ever noticed on TV or on a film, you sometimes get blocky colours, especially if it's if you're watching satellite and it's a cheapo channel that hasn't paid for a lot of bandwidth. They'll have to compress really heavily, and you'll see artifacts. If you watch scrolling text going across the bottom of a screen and you're not in high definition, you're just standard definition TV channel, you'll see loads of artifacts scrolling around with the text, because what it's doing is averaging white text on like red background or whatever they're using. So you get like blobby effects. And that's because they're averaging. Because they're saying, oh, we don't need every pixel, let's average some of these pixels out. Okay. But yeah, all the information about how many channels, what the sampling frequency is, how many bits for each sample, that all goes along as metadata. So the file isn't just the data, it's the extra stuff that goes along with it. Okay. Right, that's about it. I'll stop that bit.